Hello everyone, my name is Veli Ozdemir. I am a PhD student at University of Central Florida. The topic I am presenting is the time-dependent yielding of polymer thin films under creep. First, I would like to talk about the application of superpressure balloon as the motivation of this study. They are capable of long-duration flights and can provide sustained access to upper atmosphere. The superpressure pumpkin balloon has been designed to increase flight durations up to 100 days. So the amount of data that can be collected in one balloon machine can be increased significantly. The superpressure balloon is completely sealed and pressurized in order to maintain constant altitude. The balloon is subjected to daily thermal loads and pressurization cycles. The viscoelastic nature of the polymer is an important aspect to consider during the design of the balloon. Two concerns for successful long-duration ballooning are the creep response of the material and the yielding of the polymer. The polymer shows time-dependent strain under the creep loading, risking the operation of the balloon, especially for long-duration flights due to depressurization. Polymer may also show time-dependent yielding under long-duration creep. Sustained creep conditions may cause unrecoverable deformation of the material. The objectives of this research involves viscoelastic model calibration to capture strain of the material under creep and to find the extent of loading conditions and corresponding durations that the material can undergo without obtaining permanent deformation. The material under study is linear low-density polyethylene based. It's the preferred material over other polymers because of its ductility at operational temperatures of the superpressure balloon. It is manufactured by co-extrusion of 3 layers and has a nominal thickness of 38 micrometer, and it displays slightly anisotropic mechanical properties in machine and transverse directions. The viscoelastic response of the SF420 is studied extensively before, and previously a non-linear viscoelastic model based on the free volume is developed. I would like to give a brief background on the free volume non-linear viscoelastic model, which is also used in this study. It can be considered as an extension of linear viscoelastic equations, but the shift factors are dependent on free volume. The thermal and mechanical deformation increase the free volume, and increase in the free volume accelerates the viscoelastic response. Here D is the creep compliance tensor, and the individual elements of the tensor are represented by Prony series. The out-of-plane creep compliances D13 and D23 are important since their value will change the free volume and affect the material response. In thickness direction, since the material is very thin, the creep compliances cannot be measured experimentally. D13 and D23 Prony series terms can be fitted to experimental data by treating it as an unconstrained optimization problem. Uniaxial experiments are conducted for model calibration. The test setup can be seen on the right. The test setup includes 3D digital image correlation system, MTS tensile testing machine equipped with environmental chamber. Since SF420 is transparent, only black speckle pattern is painted, and to achieve enough contrast in DIC, an LED light panel is used for backlighting of the specimens. Coupon specimens are lightly sprayed with black paint. Plastic plates are used to grip specimen without damaging the material. If it is sub-room temperature test, depending on the temperature, 20 to 40 minutes is allowed while the specimen is slacked to achieve uniform temperature field inside the chamber. This also ensures material is not pre-stressed before the test due to thermal strains. Finally, before the test, creep duration is specified. Considering the initial inflation of the balloon, the test procedure is modified to reflect real loading conditions. A typical test procedure can be seen in the figure. The test comprises 3 steps: constant strain rate loading, creep loading, and unloading. Strain rate of 0.001% is specified until preset stress value is reached. Once creep stress is reached, it is maintained for a duration of time. Then, the specimen is unloaded at a rate of 0.5 Newton per second, and at zero load, crosshead is moved back to original position. The strain field is averaged over the area of interest, which covers most of the specimen. On the right, some sample strain contours can be seen: longitudinal strain at the top and transverse strain at the bottom. Some noise can be seen at the boundaries of area of interest. The residual deformation of the gauge length is measured by caliper after 24 hours of free recovery at room temperature. The following figures display the result of model calibration by optimization of out-of-plane compliances with the experimental data. The second objective of this study requires observation of yielding at various temperature and stress levels. In this study, we would like to know when the material will yield under specified stress level. Checking for unrecovered deformations is the most suitable method for determining yield points. For the determination of yield points, the following procedure is adopted. For a fixed temperature and creep stress level, several experiments are carried out with varying creep durations. To illustrate, figure shows graphs of 3 different tests conducted at 6.5 MPa at room temperature. Corresponding residual strains are also noted in the graph. It is clear that as the creep duration increases, the residual strains increase. We are interested in creep duration that results in minimum non-zero residual strain. The onset of yielding was accepted as creep duration resulting in 0.5% residual strain after 24 hours of free recovery at room temperature. Yield points are explored for different temperature and creep stress levels by varying creep durations as explained in the previous slide. Figure shows the current best estimates for the yield strain at 2 temperatures and various stress levels. In this figure, the yield strain is defined as the strain at the end of the test that corresponds to 0.5% residual strain. Investigation of the initial data display increasing trend of the yield strain with increasing stress level. Also, yield strain decreases at lower temperatures. The time to yield increases with decreasing stress level at the same temperature. A yield criterion is needed for different temperatures and stresses, and also for variable loading histories. The objective is to determine a yield criterion that can be used for varying temperatures and stress history. Therefore, 2 criteria employing energy are investigated. First one is total work of deformation during the test. It is simply the area under the stress-strain graph. It can be advantageous since no model is required. For the current yield point estimates, following figure is obtained. It displays total absorbed energy history for tests at room temperature at different stress levels. The final values are of interest, and it can be seen that no unique value of the total energy at yield points can be observed. Only some portion of this energy is stored while the rest is dissipated. It might be useful to explore stored energy in the specimen, which leads us to a second energy criterion to be explored. The second energy criterion investigated is the free energy approach. Free or stored energy is the energy stored elastically in the material. Under the creep condition, the stress carried by elastic components increases over time. It was postulated that yielding occurs when the total stored energy in the elastic components exceeds a limiting value. For this criterion, the calibrated model is needed to calculate the free energy. The calibrated free volume nonlinear viscoelastic model can be used to calculate free energy during the experiment. Preliminary data shows that free energy at yield decreases with decreasing stress. Application of free energy criterion fails to provide a single energy value at the estimated yield points. In summary, free volume nonlinear viscoelastic model is calibrated. Experimental procedure is developed for determination of yield points under creep. Preliminary data shows that time to yield increases with decreasing stress level, and the yield strain increases with increasing stress and increasing temperature. 2 energy-based criteria are tested, but a unique energy value corresponding to the yield points is not observed. This is an ongoing work, and here preliminary results are presented. The future work will include more experimentally observed yield points at colder temperatures, and the focus will be placed on developing a yield criterion capable of predicting yield at varying stress and temperatures. Also, an isotropic nature of the material must be taken into account in the criteria. The authors would like to thank NASA Balloon Program Office and TANSYS for helpful comments and discussions. Thank you for your attention.